Welcome to tutorial 3, combustion. So we have another question. It's a slight modification from tutorial 2. Okay, this is how the question goes. Butane is burned with 20% excess air. From 100% conversion of butane, 80% of that conversion produces CO2 and 20% of that conversion produces CO. Find the molar composition, dry composition of the product gas, and you are given 100 mole of butane as your basis. Okay, first of all, to start this question, you see, you have this information, you have 20% excess air. It's not theoretical air, but you have excess air. And then 100% of conversion of butane, but from 100%, 80% produce CO2, 20% produce CO. That means we have two reactions here. One reaction is the complete combustion that produces CO2 and water, and the other one is partial combustion which produces CO and water. Okay, so we have two equations, so we have to write down the equation. So these are the equation that we obtain for these two process. We have two reaction because this information. Okay, now we have CO2. If in your question is mentioned about CO, that means it's not one equation that you have in this process, but you have two. You have complete combustion and also incomplete combustion. Right, and now from the reaction, we draw, after we completed the reaction, we draw the process flow diagram. So, we know we have to write down our basis. So, our basis is 100 mole of butane fed into the furnace. So, we have to write a complete sentence of it. So, and then we draw our furnace. There will be 2 feed line into the furnace. Okay, 1 feed line is for our fuel, butane, which is 100 mole. And then we have another line of our, another reactant that is air. But we split this air into a number of mole of O2 and number of mole of N2. Okay, if you total up the number of mole, you get the total number of air. Right, and then the product goes out. Let's see. So how many product that goes out? We have CO2, we have CO, we have water. Okay, and then because it says 20% excess air, so you expect to have O2. Do we expect to have butane? No, because butane is 100% convert, so there will be no butane. But we expect N2 to be out here as a product. Okay, remember our objective is to find the molar composition, dry composition of the product gas. When you do reaction, so better perform the calculation in terms of mole. Okay, you should do, it's not better, I would say you should do the every calculation in mole. Okay, so now we want to find the unknowns. The easiest one, because we have many information about the excess air. The easiest one is to find how many mole of O2 in, based on the information. So we find NO2 in first. So to find this, we need to use the theoretical oxygen equation. So based on theoretical oxygen, if we have feed of fuel 100 mole, then we times it with the conversion factor based on the equation here, the main reaction equation. So we have that we require, if we have 100 mole for a complete combustion, we need 650 mole of O2. So always find your theoretical oxygen just based on the main equation, the main product equation, yeah? So your theoretical O2 always based on the main reaction. So you know, if you have 100 mole goes in, you require 650 mole of O2. So from this information, you can find how much is O2 that goes into process, the actual O2 that goes in, because you already know that your excess air is 20%. So we use this, we times with this ratio, what this fraction, this information that we will know. So 1.2, or actually 1 plus O2, 1 plus 0.2, so we get 1.2 for the excess value, times by what? 160 mole of O2 theoretical. So we'll have that O2 that goes in is actually 780 mole O2. From this information, so we can find number of nitrogen that goes in. So we still use that the equation of O2 here, but we have to time it with the ratio of nitrogen with oxygen. Then we'll get number of mole of N2 is 2932.8 mole of N2. Okay, so we have obtained N2 in, which is equivalent to 780 mole of O2. So we N2 in is 2932.8 mole. N2 out is equal to N2 in because it does not react, so you'll get N2 out equivalent to 2932.8 mole of N2. Now let's find CO2 out and also CO, because we are given this information, 80% of butane converted into CO2 and 20% converted to CO. So we use this information to find number of CO2 out and CO out. So CO2 out will be 0.8 times by 100 mole of C4H10, and then we times with the ratio of CO2 produced with with the butane that fed into the process. So we obtain CO2 out equivalent to 320 mole of CO2. So this is our product, CO2 equivalent to 322 mole. For CO out, we know 20% of that conversion produces CO. Okay, so we know 0.2 times by 100 mole of butane times with the ratio of CO produced with mole of butane fed. So we obtain 80 mole of CO being produced as side product in this process. Now we like to find the remaining unknowns, that is O2 and also H2O in the product line. So we will use extent of reaction. So we have to get the extent of reaction 1 and extent of reaction 2. So if we use CO2 balance, since we already know how much of CO2 out, we use CO2 balance to determine extent of reaction 1 for the main reaction. So we know out is 320 mole equivalent to 0 produced plus 4 times extent of reaction 1 plus, because it's a product, so you obtain the extent of reaction 1 equivalent to 80 mole. Okay, and because both O2 and H2O are in equation 1 and equation 2, we also have to find extent of reaction 2. So we use CO balance, the easiest one to obtain extent of reaction 2. We know CO produced is 80 mole equivalent to 0 in plus 0 in plus 4 times by extent reaction of 2, then you get your extent of reaction 2 equivalent to 20 mole. Oh, just now I think I made a mistake. This is feed, right? So feed for CO2 is 0. So okay, so now you obtain extent of reaction 1 equivalent to 80 mole, extent of reaction 2 equals to 20 mole. So now we can find O2 and also mole of O2 out and also mole of H2O out here. So now we find O2 balance since we already have extent reaction 1 and 2. So we use we find O2 balance which is here out using the extent of reaction. So we do not know what is the we do the O2 balance. So O2 out is equivalent to 780 that goes in, that fed into the process, minus 6.5 times extent of reaction 1, minus 4.5 times extent of reaction 2, because O2 is being used in 1 and 2, reaction 1 and reaction 2. So this is 6.5, this is your 4.5. So when you do the calculation, you'll get your O2 being unused or balanced that goes out into the product stream is 170 mole O2. And then, since we want to find the water that produced from the process, we do the H2O balance. We know water out or water being produced equivalent to water that goes in, which is 0 because we do not have water in our product line, plus 5 times extent of reaction 1 because from the reaction 1 and it's a product, plus 5 extent reaction 1 plus 5 extent of reaction 2. So you obtain the value of water that goes out or produced from the process equivalent to 500 mole H2O. So basically we have obtained the all information at the product line. So this is using extent of reaction, but actually you can use atomic balance or molecular balance to solve this to get the information as well. So we move to the final step, that is to find the molar composition, dry composition of the product gas. So we have to find the total number of mole at the product gas in terms of dry gas. So our product actually contains water. So however, if we need to find dry molar composition, we have to exclude water from our total mole of product gas out. So we just add to find the total number of mole at the product gas out in terms of dry product. We just add a number of mole of CO2 with number of mole of CO, number of mole O2, and number of mole of N2 that we have at the product line. So in total we have without water is 3,502.8 mole of product gas without water. So to find the composition is easy. We just divide, let's say for this one, we find the molar composition for CO2, number of mole of CO2 that comes out at the product line, divide by total number of mole, dry mole. Then we get the molar composition for CO2 is 0.091. If we times by 100, we'll get the unit in terms of percent. So this is 0.091 mole CO2 per mole, or in percent will be 9.1% CO2 in this product line. As for CO, 0.023 mole CO per mole, or 2.3% CO. And then we have, this is for O2, or 4.9% O2, and finally we have 84% of N2, or in terms of fraction we have 0.84 mole N2 per mole. This is how you write down the unit if you leave it in terms of mole fraction. Okay, this is how you find the molar composition of your product in terms of dry gas.